Millions of users type billions of keystrokes every single day, expecting search suggestions before their fingers even leave the keyboard. Returning a result within a 10-millisecond window requires processing this massive stream with zero wasted motion. In 1998, a search engine's index was tiny. This latency requirement was easier to manage, as the data fit on hardware with severe memory constraints. This structure is a prefix tree, or trie. It organizes characters into branches. If you type the letter B, the tree branches to A, and from there it splits down into terminal words like bat, ball, and bath. When a user types a prefix, a standard algorithm attempts to traverse the structure. It must scan down every possible subbranch to evaluate all the terminal nodes, sort them by weight, and determine which popular terms to suggest first. But as the English language index reaches tens of millions of phrases, this approach collapses. Evaluating millions of possible paths at runtime requires heavy computation, creating a latency bottleneck that prevents real-time results. Relying on real-time computational traversal is structurally incompatible with the sub-millisecond response times required for a viable autocomplete feature. To eliminate that computational delay, the system relies on a technique called top-K precomputation. Instead of searching the lower branches to find the heaviest weights, we modify the parent nodes themselves to permanently store a pre-sorted array of the most popular terminal terms directly inside each specific prefix node. Now, when a query for BAA arrives, the system does not traverse the tree. It instantly reads the pre-populated array at the immediate node and fires the result back to the user, bypassing the compute time entirely. However, solving the compute problem creates a severe storage crisis. By packing arrays of complete strings into every junction of the tree, the memory footprint of every individual node swells. Physical hardware limits the size of these structures. A single server cannot hold a globally scaled English language trie augmented with these heavy top-K lists. Achieving zero latency reads requires so much memory that the monolithic trie structure must be shattered and distributed across a cluster of independent machines. To manage this distributed architecture, we have to enforce a strict boundary between our high-speed read path and our heavy-lifting write path. This diagram illustrates the read path. We start by taking the oversized trie and mathematically partitioning it across multiple servers based on alphabetical prefix ranges. The data is split into blocks, like A through K and L through Z, each hosted on its own dedicated cluster. To keep track of where everything lives, a configuration manager called Zookeeper steps in. It maintains an exact, highly available map that connects specific alphabet ranges to their designated redundant hardware. When a user fires off a keystroke, that request first hits a load balancer, which queries a distributed memcached layer. If the prefix is not cached, the system must locate the authoritative data. The request then queries Zookeeper, retrieves the correct routing address for that specific prefix, and shoots directly into the appropriate node cluster to grab the pre-computed array. If a specific subset of the alphabet sees high search volume and a cluster becomes overloaded, Zookeeper dynamically splits the overwhelmed range into smaller segments to distribute the traffic evenly. This architecture operates as a heavily cached, dynamically routed lookup table, bypassing the computational cost of traditional search algorithms. A lookup table is only as useful as its underlying data. We must manage the live queries and determine how top-K weights are updated. This is the right path. Every search phrase typed by millions of users streams continuously into a fleet of aggregator nodes. They use consistent hashing rules, ensuring specific search phrases are always batched by the same node over a set window of time. Periodically, aggregators push this batch data down into a Cassandra database, optimized for writing heavy time series data. Here, real-world traffic is distilled into strictly structured rows, logging the specific search phrase, the precise time interval bucket, and the aggregated sum of weights. Bucketing the queries by time interval allows our algorithms to apply mathematical decay. This ensures that a current trending topic is ranked higher than search volume from several months ago. The write path acts as an asynchronous shock absorber. It transforms noisy live queries into structured data, isolating volatile processing from production read nodes. We now have a high-speed read cluster and a heavy historical database, but we need a mechanism to connect them. This is handled by a set of dedicated worker components called appliers. The applier wakes up on a strict interval, every 15 minutes, to execute heavy offline computations. It connects to Cassandra and pulls all the time-weighted phrase data corresponding to its specific alphabetical prefix range. Using that data, the applier runs the algorithms to calculate the new top K rankings and assembles an entirely new Trie shard locally inside its own memory. Once the build is complete, it performs an atomic swap. The applier pushes the newly constructed Trie up to the live cluster, seamlessly overriding the old shard in a fraction of a second, without dropping a user read request. This architecture decouples the complex data compilation from the real-time user requests. The most expensive computations are safely shifted offline. Even with perfect backend orchestration, a request still takes time traveling through fiber optic cables. We must contend with the physical constraint of geographic distance. If your main data centers are centralized, a user typing from an edge location like Seattle will experience network latency on every keystroke. To combat this, we push the pre-computed data closer to the user. Content delivery networks intercept queries for highly popular, localized prefixes before they ever reach the main backend. We optimize further by moving data onto the user's machine through client-side prefetching. When a user types BA, the edge server preemptively bundles likely next keystrokes, like BAT and BAL, into the browser's cache. Heading T instantly pulls the local array, eliminating the network trip. Designing for billions of users demands a focus on relentless offline pre-computation, architectural decoupling, and pushing data as physically close to the user as possible.